Howdy. This is the presentation for the Hardware Trojans and Third-Party IP project. It's by Adriana Nunez, Dana Billman, Kathy Vo, and Sophia Martinez.
All right, so I'm Sophia Martinez and I'll do the motivation slide. So let me begin by explaining the motivation behind our project. The development and fabrication of system on chip, or also known as SoC, has become a globalized process. While this brings cost benefits, it also introduces significant risks. And one of the points I made here is that one of the most concerning threats is the insertion of hardware Trojans, or HTs, which are malicious modifications to the hardware design um, th- that a lot of companies have. So these can compromise the functionality of the hardware and potentially lead to sensitive information being leaked. So that would cause a lot of worry. And why should we worry about Trojans? Well, first, they can expose critical or confidential data, jeopardizing the security of entire system. Second, they can disrupt the intended functionality of hardware devices, potentially causing um, things like malfunctions or failures in critical systems. This is why detecting and mitigating this risk is a crucial focus for this project. Next slide, please. And another motivation is how we relate to the course. How does this connect to our course on embedded system security? Well, the goal that we worked on is to enhance the detection of hardware Trojans through an innovative technique we call GNN4TJ, which utilizes graph neural networks, and this is directly tied to the challenges faced by many embedded systems today, as these systems are integrated to a wide range of applications, from IoT devices to automotive systems, which we see everywhere. And next point is the techniques we're employing in this project, or we employed, are aimed at improving security for embedded systems by automating the detection of malicious modifications early in the design process. Through this, we not only address a critical threat, but also advance our understanding of security techniques for embedded systems, aligning perfectly with the course.
Hello. Setting up this project, we used the Olympus server and Conda to create our environment, which we titled Lab. And then after we created the environments, we were then required to install the necessary packages, such as some of the packages that we installed were the PyGraphics and PyTorch. And after we installed the necessary packages, we then had to navigate into the homework to directory and then into the examples directory to finally run the script. This project required us to use two different model graph scripts, which were AST and DFG seen below. This project required us to run multiple trials of the models. We were then required to change the hyperparameters in the file titled example GNN4TJ to see how it would affect the accuracy of the model. And then in the next slide, we have the implementation of our project. And we use the command script. We use the command script, DFG, and AST graphs to train the model with the toy dataset. The command listed below produces the loss, accuracy, F1 score, precision, and recall of the graph, which were all related to the model's accuracy. We then use the unknown horse Trojan detection method for this project. And that is basically running each base circuit 10 times and seeing how often true positive, false negatives, and false positives appear. Once we ran the initial 10 trials, we could then use the results to obtain the ideal variable values, which are seen in figure 1. And then after we edited and implemented the ideal variable values into the previously GNN4TJ file, we were then able to produce the results seen in the next slide.
So our results came from running multiple tests with multiple variables, and from these we learned several pros and cons from using these GNN40J technique. The pros is that for both small and medium size testing, this works very well because it doesn't, those small PCBs don't require many data sets or lots of computation. Its F1 scores are equal in distance between precision and recall, which is good because you want something that balances both. Its accuracy is above 0.7, which is a standard for machine learning, and it is above in both DFG and AST files. And finally, it simplifies the analysis and gives graphical representations, as you can see on your right. Some cons is that this doesn't work well for larger sizes. It requires lots of data samples and is heavily dependent on processing. So it requires lots of computational powers, which means it takes much longer and much more power, which is technology that's not easily attainable or is not created yet. It's also heavily dependent on tool chains, which requires multiple data and lots of power to run. From the testing and variables we used previously, we calculated its precision, recall, and F1 values, which is a standard among all machine learning techniques. This uses true positive divided by true positive plus false positives. Same with recall, true positive divided by true positive plus false negatives, etc. These requirements had to follow the standard machine learning requirements. So accuracy had to be above 0.7, and its F1 score had to be in equal distance between precision and recall. On the right, you will see the final variables, which we determined were the most ideal after running multiple variables. As the AST, all accuracies were above 0.7. As well in the DFG, they were all above 0.7 except for the testing and best. The F1 score also was right between the precision and recall between every test, which is good to balance and mitigate what is required.
Next, we have our demo video. So for every time we wanted to go in, we would change the values, and then we would run it. So the values that we were changing were the learning rate, the seed, the epochs, the hidden dropout, batch size, number layer, test steps, pooling type, readout type, ratio, pool ratio, embedded dimensions. Each of these we would change one by one, and then as we could see, it would just run. And so every time we would run it, it would come up with different data. So that was how we ran the experiment, and like I said, changing the one variable at a time helped us be able to understand the results better. And then we did this for both DFG and AST just to see the difference between the two types of graphs.
All right, so I'll conclude with a summary. How this project improves upon what we learned in the project was first, we extended the foundation knowledge of embedded system security by implementing an advanced methodology using graph neural networks, also GNN. And unlike traditional approaches, we process hardware design into graph formats, which personally was the first time I did that kind of stuff. Specifically, data flow graphs and abstract syntax trees, which allowed us to model the hardware's behavior more efficiently. And also, um, for the next point, using the HW2VEC tool, we automated the pipeline for pre-processing our LT code or RTL code, transforming it into graph representation ready for graph-based learning. And this step was crucial for streamlining the process and making detection faster and more efficient. Additionally, we evaluated our model by using matrices such as precision, um, the F1 score to ensure accuracy and reliability. And overall, our approach not only builds upon, but only significantly enhances the concepts from the course, addressing real-world applications and security embedded systems and improving the detection of hardware Trojans in a scalable and practical way. Thank you.